Howdy folks, welcome to week 3 homework. You'll notice that we don't have too many slides here, and I'm going to try and keep this down to the 20 or 30 minute mark that we talked about in previous classes. This time we're handling repeated measures ANOVA and data management. Okie doke, so what is a repeated measures ANOVA? You might be surprised to hear this. It's an ANOVA that handles repeated measures data. What exactly is repeated measures data? You may remember when we did our dependency test, we handled repeated measures data for the most part. Repeated measures data is any data that comes from the same person, usually at different specified times. So let's measure the height of a person at age 14 and 15. Let's measure the intelligence of a person at 12 a.m. on Monday and 5 p.m. on Tuesday. Sometimes the data is not exactly as time sensitive as you might think. Remember when we did our dependent t-test, you can have data from, say, a mother and a daughter, and while that data is not like a time-oriented dependent association, it is sort of related data, and you could do a dependent t-test, and you pretty much could do a repeated measures t-test, ANOVA there. However, for the most part, repeated measures ANOVA is always going to deal with data coming from the same person, coming from a within subjects design. One situation where you might not be sure about using a repeated measures ANOVA is when your within subjects design does not have a time factor to it. So a time factor analysis or very obviously repeated measures ANOVA would be, okay, you're going to take the 3 tests, one today, one tomorrow, one the day after. They're going to be tests A, B, and C. So there's a clear day 1, day 2, day 3 thing going on there with those 3 tests. It's a clear repeated measures data point. However, let's say that you were working with counterbalancing those tests. And they took all 3 of those tests in one day, and not exactly in the same order. So they could take test A and then C and B, or BAC or CBA or whatever. That's not necessarily a time-sensitive repeated measures, but it is definitely a repeated measures ANOVA independent variable, because you're getting the same person to give you data multiple times. So just be wary that both of those cases definitely warrant a repeated measures ANOVA. That's something that confused me when I was starting out here. So there doesn't necessarily have to be an order to the data points. In fact, you could, if everyone has a different order they take those tests in, one person takes BAC, another person takes CAB because of counterbalancing or whatever, you can still use this repeated measures ANOVA to see, okay, well, was test A harder than test B overall? Now, if you want to care about the order, the specific order those tests were taken, you could do an analysis with just test 1, 2, and 3 and ignore the version. You could do a repeated measures ANOVA, that's test 1, 2, and 3, but also test A, B, and C. So you could mix and match both the within and between, or the repeated and non-repeated factors there, or the repeated or the time and version things there, and you can have those be 2 different independent variables. That's starting to get a bit confusing, so let's get back to repeated measures ANOVA. What do the repeated measures ANOVAs do different from a regular ANOVA? There's kind of 2 main time points there, 2 main factors there. First, repeated measures analysis of any kind is always going to be a bit more liberal. Things are going to be a bit more significant there. And the other thing is that a repeated measures analysis allows you to handle related within variable errors. What does that mean? Well, let's say that you have a normal situation where you're dealing with the independence of independent variables assumption. In that case, you want variable 1 and variable 2 in your analysis to be independent of each other. So if you're measuring, say, how tall are people depending on their socioeconomic status and age and socioeconomic status probably won't be related to each other. But if you were measuring how tall people are based on their socioeconomic status and, say, maybe like a race variable, those 2 variables are probably going to be related to each other depending on the country you are and the sample that you're working with. So you may need to include both of those, but be wary of the independence of the 2. You may choose one over the other. You may just choose to include both of them and see if they actually do completely different things. Depending on the dependent variable, depending on what you're working with, it could be dangerous. With a repeated measures analysis, we're working with a slightly different independence problem, independence within the variable. So let's imagine this scenario. Let's say you're comparing the heights of people who have different favorite colors, green, yellow, red, blue, orange. Those different conditions of color favoritism are not going to be related to each other at all. There's no particular reason why those would be connected to each other. However, if you look at, say, the heights of a person at age 14, 15, 16, 17, within the variable of that age, you're going to have a consistency to it. Any one given person could be consistently under height or over height compared to the average. And because of that consistent difference from the normality of a random sample, you can come up with some assumption problems. And so repeated measures analysis helps you deal with that. And part of the way it helps you deal with that is with that more liberality. If that's confusing, it's more important to understand this than it is to understand that. Okay, how do we run that repeated measures analysis? Running it is actually not too complicated, but you need to have your data in the right format. We're going to start by looking at a long data format, which is what we normally handle. So we're going to go to Jamovi and find in the R datasets folder the loblolly file. Bring it up, open up a new Jamovi file. Here we go, nice and fresh. And we're going to open up from Open Data Library. Make sure you go to the R datasets thing. If you're in another folder, you can click up the up arrow. Find loblolly, it's a little bit down. And this is the data about the growth of loblolly pine trees. Very exciting. This is a long format. Why is it called long format? Because the repeated measurement is in this long, sometimes called tall format. We have heights for a bunch of different trees. Here's tree 1, tree 3, tree 5. And we have their heights at different time points. The wide format is going to do something a little different. In the wide format, we're going to kind of mix height and age so that they're one variable. And we're going to see that we're going to have a height variable at age 3, and a height variable at age 5, and a height variable at age 10, and so on and so forth. Age 15, age 20, and age 25. Okay, now another thing about these variables is that they're all nominal, and we definitely want them to be continuous because height is a continuous thing. We also want to make sure that these are, well, let's do that. We also want to make sure these data types are decimals because data points as a decimal. Now, I could go through and change all those one by one. That's going to take a long time, so instead I'm going to show you the quick way to do it. Select all of these by shift-clicking, and you'll notice that you can now set all of them to continuous and all of them to decimal. Notice here it's white because there's nothing consistent. One of them was decimal in the R3 integer. We're going to put all of them on decimal. Now it says decimal. Now we're good to put our data there. How are we going to get this data from here over there? We could copy one by one, which would take forever. So we're not going to do that. Instead, I'm going to show you a little bit of a faster way to handle this using Excel. So let's first copy all this data. Okay, data's all copied up, right? Yep. Hit Control-C or right-click and copy. Open up an Excel. Get a new Excel file, and we're going to pop this data in here, one row below the top, because we're going to give the top a series of names, such as height, age, and C. Messed up height there. Whoopsie. Okie dokie. And now we're going to put in the names of our new variables here, just the same way that we've done here. Quick trick with naming things or copying information. If we put in a variable here like h3, this little box here allows us to drag and copy. Because we've given it a variable name, the Excel can tell that we kind of want to call it as we would want to count. If we didn't want to count, we could put in h3 here again, and it would know, okay, we're just copying this over, so it's just going to copy it. But we want to do something different. We want to count by 5s only after that first variable. So if I put h5 and h10 there, select the two, copy them over, get rid of the extra stuff, and we've got H3 through H25. That's obviously much more useful if you have a much longer or taller thing that you need to do there. Now, here's the fancy tricky part. We're going to take this data, select it, and organize it in a way that'll make it a lot easier to copy, paste from here to there. What you're going to do is transform the way the data is organized. You'll see that right now we have data from seed, the first seed, all 5 of those data points, 6 of those data points, and then the second seed, all 6 of those data points, da 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 da. But what we want is to have all of the seeds in a row, so that one row equals one seed. So what we're going to do is select all of this, go to Data, Sort, and we're going to first sort by the repeated measures variable, age. Note that if this box here is not selected, it's going to consider the whole thing the data, and this stuff's going to get sorted along with the numbers. You don't want that. Let's keep it selected. We're going to add a level and also sort by seed. You don't necessarily have to do this, but it can be helpful too. So when you hit OK, watch what happens to these data points. Blammo. So now we have all of the age 3 heights in each of the seeds, and the seeds here are in order. So now what we can do, we can copy this stuff over. I'm going to use Control X or cut and paste over here. Control V. Where's paste? There's paste. And we can cut this stuff, paste it there. And so those are all of our H3s. And we can go through and do that. See, we know these are all of our H5s. Paste it in. These are all of our... I'm going to go ahead and copy all the rest of the data over because it's starting to get annoying to scroll. Paste it in. Definitely still tell that these are one bunch because of the 5s are still the same amount of data points. That's there. And if you come up with a consistent amount of data points, you have the same length row here, then you should be good. Rightio, so that's a much quicker way of copying this stuff than copying it one by one, which would be, in French terms, a pain in the ass. Let's go ahead and copy this data back into our Jamovi. Whoops, back into our Jamovi. Make sure to put it in the right place. And now we're good to go running that repeated measures ANOVA. Before we do that, I will run regular ANOVA just to see if we can spot any differences from the regular ANOVA to the repeated measures ANOVA. Independent variables height, dependent variables age. It needs to be categorical. Let's do that for you. I don't know if you can hear my stomach, it's grumbling. We're going to ask for a eta squared. And here's the stuff we got. Let's take a quick look-see here at the graph. Looks like all the data points are very different from each other. So I would expect all the post-hoc tests to be significant. Yep, everything's significant. We don't even need to talk about it. All right, so now let's run that repeated measures ANOVA, and we'll come back to these results here in a bit. Okie dokie. So, what have we got here? Things looking a bit confusing. Let's start off just looking at each one of these boxes and briefly stating what we're looking at. These two boxes are going to handle our repeated measures variable. This is always going to be our dependent variable as well. We're going to name the factor here by the repeated measures thing, so that's age. And we're going to start putting in the ages that we're talking about, 3, 5, 10. Now, you'll notice there's another box here for another repeated measures variable, and you can have multiple repeated measures variables. We're not going to work with this right now. We'll see it in class, so don't worry about it too much. But it's there. Now, you'll notice that we now have 3 boxes for data. We can start putting in that data one by one, but we won't have anywhere else to put the rest of our repeated measures data. What's going on is that in this first box, we have to say how many data points we have, how many levels of a repeated measure we have. And so we're going to go ahead and finish labeling that, and as we do it, you'll see that more boxes appear in this data box here. You can finish putting that stuff in. Fun fact, if you just highlight them all, you can put them all in one go as long as they're in the right order. Proper naming will prevent you making any mistakes there. It's very obvious which ones of these should be which. Here we have the boxes for our independent variables. Right now we're not using any between subjects variables or between subjects covariates. This means between subjects nominal or categorical variables. This means between subjects continuous variables. We have a place here to label our dependent variable. It's just a label for the graph. So if we go look at the graph, which should look pretty similar to our previous one, let's see what we got. Looks almost exactly the same. Scale's almost exactly the same. The widths, or sorry, the size of the error bars here is still pretty dang teeny tiny. Can you see any differences between these two graphs? I can't really see much of a difference, so we'll skip out for that for now. If the data that we were working with were a little bit less clear, you may see a difference in the graphs, but really for now, we don't need them, so we're going to get rid of them. Let's just stick with the output. Oh, sorry, I forgot to mention. In this graph, we've got age, because we named age up here, and we have age here, x variable, independent variable. Here it just says dependent. So if we name it height, hit enter, it will change to height, so it's easy to tell what we're looking at. But again, don't care about the graph. That's just all that does. Now, we get a new type of eta squared here, generalized eta squared. Generalized eta squared is best when you're doing a repeated measures ANOVA that involves both a repeated measures independent variable and a between subjects independent variable. We'll just ask for it right now. It's not going to be super useful, but let's just see what it looks like. And now we can compare our ANOVAs. You'll notice that the output for this ANOVA is pretty much exactly the same as the output for this ANOVA. The only real difference between the two is that our F statistic has a different number on it. What's going on? Well, number one, you can tell that reporting your repeated measures ANOVA is pretty much going to work the same way as reporting your regular ANOVA. The only difference that we see, that F difference, is that liberality I was talking about earlier. In this case, stuff was hella significant, so our p-values are both exactly the same, and our effect sizes are exactly the same. However, if we had an analysis that was a little bit less significant, less obviously significant, remember eta squared here, just to give you a reminder, small, medium, large eta squareds are 0.01, 0.06, and 0.14, so a 0.99 eta squared is considered ginormous. If we had a less ginormously significant analysis, the difference in these F's would mean night and day on the significance p-values. We also get in the repeated measures ANOVA a between subjects box here. Well, we don't get that in the regular ANOVA. What's going on in this between subjects box is pretty much the same as what would be going on in the ANOVA. This is where the different math is. Why do we get a residual for this between subjects box? Why do we even have a between subjects box if we have no between subjects variables? Well, the fact of the matter is we do have one between subject variable. We haven't really talked about it, but we have got it. The between subject variable is the fact that there's different trees in this analysis. So tree 1 is a between subjects variable from tree 3 and 5 and 7 and whatever. But because it's not a variable that we're really measuring, it's not even included here. And if we wanted to measure it, we could pop it in. We could. But it would be a little bit of a silly thing to compare, because then we're just seeing we're seeing whether or not different seeds have different heights to them, which isn't necessarily what you want to talk about. Do you really care about individual differences in this analysis? Probably not. In some cases you might, and there's also better ways to run that individual differences thing that's going on here. You'll notice that when we added that in, it's a teeny tiny effect. For the generalized eta squared, much bigger, but still not quite significant. Probably not quite significant because their sample size ain't great. We only had, what was it, like 14 different trees that we were working with. What this has also done, however, is changed the stuff here for age. Age is still significant, but you may remember that the eta squared was a bit bigger. Now it's a little bit smaller. And that's okay, that's okay. This generalized eta squared is good here because we can compare this on equal footing across these three effects that we're looking at. And we can also see that the interaction between age and seed, the between subjects thing, is included here and can be analyzed there. I'm not going to talk about that a whole lot, but I mean, that's pretty much the whole kit and caboodle already. I said I'd wait for that for class, but I tend to meander on, and we're at the 20-minute mark, so let's keep going. How do you write this report? I'll just say it for you because it really is very simple. A repeated measures ANOVA found a significant effect of age across for predicting, or found a significant effect of age on the height of loblolly trees, parenthesis, stats. And we could look at the post hoc tests, but I know they're all significant. Tukey's post hoc tests found that each tree height was taller than each other tree height at different ages. And really what would be helpful here is just a table with the means and standard deviations for each of the heights. Okay, so let's move on to the second part of the analysis here. We've already talked about the report. Let's talk briefly about checking your data. We haven't spoken about this too much so far, so I want to talk about it just a little bit. How do we deal with our data being messy? How do we check if it's messed up? How do we check for outliers? And what do we do if we find those? Often typos happen and outliers can be dangerous, so let's see if we can figure out how to find them. Now, the best way to do that is to go to Exploration and Descriptives. And if we pop in our dependent variable there that we were working with back in our normal ANOVA, we'll get some pretty quick descriptives here: mean, median, minimum, maximum. I know that for a height variable, minimum should be higher than 0. Looks good. Maximum should not be like way higher than the mean. Looks good to me too. We can ask for useful plots. Histogram. Let's see if things look normal. Could be better. Definitely there's some funnier stuff going here, probably because these are the earlier ages and things grow faster, say between age 5 and 10 than they do between age 3 and 5 or any of the other ages. Stuff doesn't look super normal, but we know that this is an age repeated measures data set, so things are kind of funny. Look at the QQ plot. Do things look normal? There's definitely a bit of a logarithmic curvy thing going on here, and we can see that each of the ages has its own little section as well, but not too bad considering the data that we're working with. If we separate this data out by age, it should become a little bit more normal looking. Look at these histograms. Definitely looks a lot more normal, no real outliers. Look at these QQ plots. Definitely looking a lot better, especially at this later stage. Okie dokie. So how do we check for outliers? You got a couple options. In your histograms, go back to the basic histogram we were looking at earlier. If there's an outlier, it's going to be very separated from the data. Now these kind of look like they might be outliers, but they can't be outliers because there's quite a few data points there. We were looking for just a tiny little bump, 1 or 2 points worth of data that's farther away from the data. If we ask for not a bar plot, I want a box plot. If we ask for a box plot, an outlier is represented with a circle outside of the bounds of the box plot, and so we're seeing no outliers here. If we had an outlier, I'm just going to go in and mess with the data. Let's say that we have an outlier of, say, negative 20. That's not a ridiculous outlier, but we can definitely see it's just one little data point that's separated from the rest. This box plot doesn't even show it here. Let's make that a little bit more exaggerated. We'll make it negative 100. Now it's becoming more obvious. It should become more obvious here in that histogram, and it definitely is, and it's definitely more obvious here in the box plot, little dot. And it says the box plot, most of the data is over here, but there's a little moon going on. It might be a problem. So how do we identify outliers numerically? What standardized procedure do we have for checking for outliers? Usually the way things go is you go look at the mean. Let's get rid of this, ask for just the mean. And you say, I am interested in outliers, which consist of the mean plus or minus 2 standard deviations. More often, 3 standard deviations. In writing a report, things are a little bit different, but that's a common way to do it. So let me walk you through how to do that. Here we have the mean and the standard deviation. How do we check for outliers? How do we even tell if they're there? It's pretty easy in this case because we could take a look at the minimum and maximum and go, okay, well, mean plus or minus 25. So 31 plus or minus 25 is a range of minus 20 and plus 70. 5, 6, 7, plus 8, minus 20 and plus 70, 6? No, plus 70. Minus 20 plus 7, sorry, minus 20 and plus 80. My basic math skills are wanting. If we look at these minimum and maximums, we can tell, yeah, definitely there is at least one thing that is outside of our acceptable range. What do we do about that? We could go in and delete that data point, but if we have a lot of data, not a very good idea. It's also just never really a good idea to mess with your data in general. So instead what we can do is apply a filter, and this filter is going to allow us to ignore any data points we don't want to use in our analysis. So we'll ask for the histogram back just so we can see. Definitely, we got an outlier on this side. And let's just add in an outlier on the top side. We'll say that we got a data point of 333, so we got double outliers. If we go to filter, click on it again to get it back, we can set a rule here using a little bit of coding to tell the analysis, to tell RMANOVA, we don't care about these boys because they're weird. How do you do that? Well, you can type stuff out. If you're new to doing this, you're going to want to click here, pick the variable we're working with, right now height, and double click, write it out there. And we only want data for height that is, say, more than 0. I know that's more strict than our mean plus or minus standard deviation rule, but really there shouldn't be any trees with a negative height. We can add in another rule here. When you add that in, it automatically says, okay, it needs to follow this rule and that rule. Okie dokie. Once again, we're going to add in height, H-I-G-H-T. This time we're going to say that height needs to be less than, we estimated, what was it, 70? Height needs to be less than 70. Hit enter. Blammo. Outliers are fixed. You'll notice that the means of standard deviations are different now. And you do not want to do this iteratively. You don't want to do this over and over again. So, oh, the new mean plus 2 standard deviations is da-da-da-da-da, so let's get these more strict ones in there. No, that's not how it works. You just do one time over. And so if you ever need to report that you eliminated or deleted or did not analyze some data due to outliers, you would say something along the lines of data from height or outliers in height were not analyzed based off of the mean plus or minus 2 standard deviation rule. More often than not, removing data points like that is kind of frowned upon in academics, so you might use a more strict 3 or 4 standard deviations difference. You may also, however, just say, oh, we didn't analyze this data because the participant did not follow directions. And people will usually give you very, very little grief if you say that, because that's more of a theoretical problem than a numeric problem. If you ever need to use different types of filters, you can add a filter and do very, very different things. Notice that this is going to be separate. You can control these separately by turning them on and off. You can get rid of them, of course, that way. Okay, so that's pretty much going to cover everything that I wanted to talk about today, and we're at 29 minutes and 35 seconds. So I'm going to go ahead and let you go. Please have a good week. Take it easy. Try not to get too cold out there. Ciao.